Welcome. In this video I'm going to show you how you can perform a so-called Neyman Goodness-of-Fit test using Python. I'm using Python in Jupyter Lab and I'm running Python version 3.11.5. I'm not going to talk too much about if you should be using this test. There are quite a lot of alternatives, and I'm using the Neyman test as if it was a alternative for a Pearson chi-square test. There are some other variations on the Neyman test, so if you're looking for those, this is not the video for you. I have a separate video where I show you how this can quickly be done with my stikpet P library, but in this video I won't be using that. So to load some example data, I'll install pandas first, and then I can use its readcsv function. I'm loading in a data file I call GSS, General Social Survey of 2012, and A because I changed a few things in there over the past few years just for example purposes. Once the data is loaded, I actually don't need all this data. There's quite a lot, as you can see. There's 706 fields. I actually only need one of them. So let's use the marital status and then use pandas values counts just to get a quick first impression. And for example, 314 people selected divorced. Now this test can check if these values, the counts, could perhaps in the population actually all be equal. Most likely not, but let's have a look anyways. So in a separate video I discuss how this can be done with my own library, but there are other libraries that can do this, for example SciPy, and they're often hidden in a function for power divergence, because that's more a family of tests and it has a specific parameter, and if you set that appropriately you get the Neyman test. So I'm going to be loading in from SciPy stats the function power divergence. If you've never used SciPy before, you of course first need to install it. After that, it requires the observed counts, so that values counts we just did, and set a lambda, and for the Neyman we can simply say that we want it to be Neyman. So let's do that, and it prints out the chi-square value and the p-value, in other words the chance of having a result as in the sample, this 815, or even more extreme if the assumption that all of them would be equal in the population would be true. Now in this case it's far below the usual threshold of 0.05, so we would reject that assumption and then would say that there are significant differences. Stats model also has a power divergence called power discrepancy function. So of course you first need to install stats models. I didn't put the code in there, but it's pip installs stats models. And then from the stats GOF you want that power discrepancy function. This one does require to actually input the observed counts, which we already have, but also the expected counts. Then lambda again can be set for Neyman to -2, and that should give the same result. Now the expected counts, like I said, most often you simply just want to divide the sample size by the number of categories. The sample size is simply the sum of the observed counts, so I can do sum of those frequencies. And for the number of categories I can simply use the len, which is short for length, of those frequencies, and since there are 5, that should give me then the 5. I multiply this array then with that same value so that it actually has that value 5 times. Then I can use the function and say, well, I want the frequencies and the expected counts and lambda that to -2, and that should give the same result. If you don't want to use any libraries or avoid most of them, then of course we should start with the list of those frequencies should be a Python native version, so I'm going to change it to a proper list. We can remove any missing values from in there. So this is actually not the list of frequencies. This is just the list of all the scores. Remove any missing values. So if it is a missing value, remove it. And to find the exact categories, I can use the set function. That makes it into a set where duplicates are simply removed. And here we have our 5 original categories again. Those frequencies can then be found by going over each of the scores in the list and count how often each of these 5 categories actually occurs, and that should give us those frequencies we saw earlier, the observed counts. Again, as earlier mentioned, len and sum for the number of categories and the total sample size. The expected counts can quickly be created again as well. And then finally, the Neyman statistic is actually the observed counts minus the expected counts squared divided by the observed counts. So I can do that by doing a sum, that's the big E, and then say, well, for each frequency 0 to k, we're actually going to do that observed count minus expected count squared. And that gives us the chi-square value for the Neyman test, and as you can see, that's the same as we saw earlier. The degrees of freedom is simply the number of categories minus 1, so k minus 1, which is 4 in this case. And if you really don't want to use any library, you then need to create something for the chi-square distribution. That's quite complicated, so I have a separate documentation on that. And at this point, most people will simply use the chi-square distribution from SciPy-Stat. So I'm going to import chi2, and then what I want is the survival function, which shows me the upper tail values. So I can simply say SF and then use that newfound chi-square value and the degrees of freedom, and we're done. You can also add some corrections if you're interested. For example, a Pearson correction, which simply says to multiply the chi-square value with the sample size minus 1 over the sample size. So that's this one. And Williams, who actually also takes into consideration the size of the table, so k squared minus 1 over 6 times the sample size times the degrees of freedom. We have all of these. We need to add them one, and with Williams you then divide by that result. And that gives slightly different chi-square values. It's also possible to do a Yates correction. That's usually reserved only for if there are 2 categories only. There are a few small variations on this. Here's the one I'm currently using. They all agree that if the expected counts is greater than the observed is greater than the expected, you subtract a half, otherwise you add a half. It's not always clear on what to do if they're equal, so I'm just going to keep it the same then. And some will say to only do this if this is less, if the difference is less than a half, but it varies a little bit. I'm using this one up here, and as you can see, it's simply a matter of going over each of the categories, and then use if and else if for the new adjusted observed counts. Then the rest is exactly the same as before, and you get a slightly different chi-square value. Here's one function that could do it all. I'm not going to run this, and this kind of concludes then actually this video. I hope this was helpful, and thank you for watching.